Using percent composition to figure out the molecular formula of a compound. Now, this is kind of a historical thing, and we can do this a lot faster nowadays, but the point is earlier, like around 1780, they found out that, in wine and beer and things, this was the active ingredient. It was this compound that had 52% carbon, 13% hydrogen, and 35% oxygen. And then around 30 years later, a generation later, this other guy actually figured out the chemical formula. So we're going to do this a lot faster than 30 years, but we're going to start with percent composition, and then we're going to figure out the chemical formula of the compound. So in this case, it's ethanol, and that's the active ingredient in beer, and this is what the molecule looks like. A couple carbon atoms, and an oxygen atom. Here's your oxygen atom is in red and surrounded by some hydrogens. Okay, so we need the game plan. We're going to start with percent composition, and we're going to end up with molecular formula. So how do we get there? Notice that an intermediate step is empirical formula. So let's just give an example here to give you an idea what empirical formula is. Let's say my final answer is C4H12O2. Now, notice that I could divide through by 2. If I had a simplest ratio, it'd be C2H6O1, right? That'd be my simplest ratio of these numbers. That is the empirical formula. It's the simplest ratio of my actual chemical formula, okay? And that's kind of an intermediate step in getting these molecular formula answers. Okay, let's try this. And we have our game plan up here, and I think it's easy if we just jump right into this. So we have a compound that is 80% carbon and 20% hydrogen. So that's what we have. So we have 80% carbon and we have 20% hydrogen. They want us to find the empirical formula, so that's where we stop. We stop right here. We have 3 steps to get there. First, assume 100 grams. In other words, replace all the percents with G's. So we have, if we had 80% carbon, that means we pretty much have 80 grams of carbon. If we had 20% hydrogen, it means we pretty much had 20 grams of hydrogen. So first step is done. The next step is to convert to moles. Remember, to convert to moles, just divide by the molar mass. Carbon is 12.0107. 12.0107 grams of carbon in a mole of carbon. Hydrogen is 1.00794. 1.00794 grams of hydrogen in a mole of hydrogen. So 80 divided by 12.0107, about 6.66. And 20 divided by 1.00794, about 19.84. So I'm just carrying like 4 or 5 digits or so. Moles of carbon, moles of hydrogen. Okay, done. The next step is divide through by the smallest number of moles, and then write my empirical formula. My smallest number of moles is 6.66, so let's divide through by 6.66. Now I'll get my simplest ratio. So I'll have 1 mole of carbon for every 19.84 divided by 6.66, about 2.98 moles of hydrogen. So that's pretty much just 3. We got to round that up. So I have CH, and here's my numbers. C1, H3. There's my empirical formula. Got it. What is the empirical weight? Empirical weight is just another name for the molar mass of the empirical formula. So 1 times carbon, 12.01, and 3 times hydrogen, 1.01. What do you get? 15.04. grams per mole. There's my empirical weight. So what we did is, you see, now we have the empirical formula. We're trying to get this molecular formula. The first step was to calculate empirical weight, so we did it. Now we have to find this little n, because I'm pretty sure the next question is what's the molecular formula. So we need to find this n where we divide the molecular weight by the empirical weight, and then multiply our empirical formula by n. So molecular weight, they said, is 60. So n is molecular weight all over empirical weight, 60 divided, 60 grams per mole, divided by 15.04 grams per mole. 60 divided by 15.04, get about 3.99, which is approximately 4. So my n is 4. My empirical formula was C1H3, right? My empirical formula was C1H3. To get the molecular formula, multiply by n. Then I get the true molecular formula. So let's multiply it by 4. What do I get? C4H12. There's my answer. That's my molecular formula. Now, if I find the molar mass of this, I better get 60, because the molar mass of this compound is 60. 4 times 12 plus 12 times 1.01 is what? 4 times 12.01 plus 12 times 1.01. Yeah, I get 60. It works. That's the right answer. Sorbic acid is added to food as a mold inhibitor. Its composition is 64.3% carbon, 7.2% hydrogen, 28.5% oxygen. What is the empirical formula? So you know the game plan. Give it a shot. See if you can get it. So I'm first going to write these down and just convert those percents to grams. So I have 64.3 grams of carbon. I'll have 7.2 grams of hydrogen. I'll have 28.5 grams of oxygen. And just convert each of those to moles. Carbon, 12.017 grams of carbon in a mole of carbon. Hydrogen, 1.00794 grams of hydrogen in a mole of hydrogen. Oxygen, 15.994 grams of oxygen in a mole of oxygen. .3 divided by 12.0107, about 5.35. .2 divided by 1.00794, about 7.143. .28 divided by 15.1234, about 1.781. Okay, we're after the empirical formula. We're supposed to stop there. So let's just divide through by the smallest. Divide by 1.781. 5.353 divided by 1.781, about 3. 7.143 divided by 1.781, 4, and 1. So my empirical formula is going to be CHO. How many carbons? 3 moles of carbon, 4 moles of hydrogen, 1 mole of oxygen. There's my empirical formula. They say the molecular weight's 112, so what's the molecular formula? So let's divide my molecular weight by empirical weight. 112 all over empirical weight. What's my empirical weight? It's going to be 3 times 12.01 plus 4 times 1.01 plus 16, about 56.07. Divide those two, you get 2. Off by a factor of 2. So I had C3H4O, so my final answer would be C6H8O2. An oxide of tungsten, and tungsten is just element W, is a bright yellow solid. 5.34 grams of the compound contains 4.23 grams of tungsten. What's the empirical formula? So we're supposed to stop at empirical formula. So remember, with empirical formula, the game plan was you have these percents, you change the percents to grams. Well, they didn't give us percents, but they gave us the grams. So we get to skip that step. 4.23 grams of tungsten. Right? And we'll convert that to moles of tungsten. Now, what's the other element? Our empirical formula, tungsten, what's the other element? An oxide. This is what we're after. How many grams of oxygen do we have? How many grams of oxygen do we have? We know that we have 5.34 grams total. 4.23 of it was tungsten. So if we just subtract the two, 5.34 minus 4.23, that has to be the grams of the oxygen. And then we can go and follow the rest of our game plan. So the molar mass of tungsten is 183.84. And oxygen so 4.23 divided by 183.84, you get about 0.023. And 5.34 minus 4.23, divide my answer by 15.0694. The next step is divide through by the smallest. The smallest number is 0.023. So I'll get 1 mole of tungsten for how many moles of oxygen? Divided by 0.023, 3.02, which is about 3. So my final answer for every 1 mole of tungsten, 3 moles of oxygen. If the molecular weight is 487, what's the molecular formula? So my N is going to be 487 grams per mole divided by the empirical weight. So the empirical weight is WO3 is the empirical formula. So my empirical weight, WO3, is going to be what? Tungsten is 183.84 plus 3 times oxygen. 3 times 15.1234, about 231.8. So 231.8 grams per mole. So 487 divided by 231.8, get about 2.1. It's approximately 2. Off by a factor of 2. So my final answer would be W2O6. Okay, so what we are working on today is this game plan. We're starting with percent composition, and we're working our way all the way to molecular formula. So just remember a few things. One is empirical formula is the simplest ratio of the elements in the molecular formula. Good luck.